So now we're going to take this local flexibility matrix of the elbow and convert it into a stiffness matrix so it can be used to sum up with the other stiffnesses of the rest of the system and the stiffnesses of the anchors and restraints. Now, in MathCAD, you can just invert this stiffness matrix directly, but what the math here shows you is how Caesar 2 converts that flexibility matrix into a stiffness matrix explicitly. This is done for every bend in your piping system. Our work is shorter here because we're working with 3 degrees of freedom rather than the full 6 degrees of freedom. But when you finish all this math, here is the stiffness matrix for our elbow. This is in the local coordinate system ABC, and when we convert it to our global XYZ axes, here's our stiffness matrix. We're going to take that stiffness matrix and drop an anchor at the near end. That would be at this section right here, these 3 terms. And once we put that in, there's our stiffness right there. It's added to the stiffness matrix. Then we're going to displace the far end, the B end. And we're going to move it 1 millimeter in the X direction, then 1 millimeter in the Y direction, and then 1 degree, that's 1 degree, about the Z axis. So again, I want to see what my load is. F equals Kx, so F equals K times D1, F equals K times D2, F equals K times D3, and here are the numbers from MathCAD. So this is the results due to the first deflection, minus 582,977, minus 582,954, negative 494,000, 29 million. We just have two nodes, the from and the to end, from and to end, from and to end, and so on. So we can match these numbers as well. Caesar 2 run to match that. If I look at that here as well, I have to put the deflections on the pipe. I can go back to my input processor and I can add my displacements. So here we are on our displacement screen for, I'm going to specify node 20. Be sure to change this to node 20, and the values that I'm going to enter are going to match these terms here. 1 in the X, 1 in the Y, and 1 degree in the Z. I'm going to, in Caesar 2, put 1 in the X, 1 in the Y, and 1 rotation by Z. It is important to, in order to match those numbers, to lock up the other undefined degrees of freedom. Otherwise, it's free to do whatever it wants. We got an anchor at the from node, and we're specifying the displacements and rotations at this far end. 1 in the X, 1 in the Y, 1 about Z. Error check. Very clean model. And now I'm going to go to the load cases, because these load cases were built for the force sets. I don't want to use force sets. I want to put displacement sets. So I'm going to clear out these 3 cells and drop in D1, D2, and D3. Operating load case is fine. Click the running man. And here's our output screen. I'll take a look at those 3 load cases. I'm interested in the local forces and moments. I want to match the loads on the piece of pipe, 10 to 20. Loads on the piece of pipe. Here's 10 to 20. Now 20 to 30, that's just that little bit at the end of the run. So basically this is the beginning of the elbow and that's the end of the elbow. And you're going to see those are the same numbers we showed on the screen. And then the second load case, this is the vertical 1 millimeter deflection. And finally, the rotation at the end. Now, these are basically a free body diagram of the elbow itself. Of course, if I wanted stress, I could take these forces and moments and use them to calculate the stress in the pipe. Now we've completed the development of the stiffness matrix for the elbow, and we will go on to assemble that with the other straights in the next exercise. In your MathCAD printout, though, there is one more step where the stiffness matrix is inverted and that A matrix is now loaded with forces, 10 to the 4th newtons in the x direction, 10 to the 4th newtons in the y direction at node 20, and 10 to the 7th or 10 to the 4th newton meters in rotation at the far end. You can build this in Caesar 2 on your own, putting F1, F2, and F3, and you should get these same deflections of the far end. Deflections and rotations. Deflections to rotation. Again, the rotation, this is in radians, and this is how many degrees that is. So give that a try. In the next session, then, we will go on and assemble all these elements together as Caesar 2 would as well.